The world appears to us as something simple, solid, and ordered. When we throw a ball across a field, it traces a neat arc through the air, and we can point to that trajectory as if it were a fact written into reality. When a beam of light streams through the window, it seems to move in a straight line until it bends obediently upon striking a glass of water. The comforting assumption behind all these observations is that nature chooses one path, one definite history, and follows it faithfully. For centuries, this idea of singular trajectories ruled physics, embedded in Newton's laws of motion and in our intuitive grasp of cause and effect. Yet hidden beneath this surface of clarity lies a different truth, one that quantum mechanics has revealed in ways so startling that it still unsettles even those who dedicate their lives to physics. The truth is that nothing in nature truly commits to a single path. Instead, every particle, every photon, every electron explores all possible routes simultaneously, as though reality itself is a vast computation of every conceivable way events could unfold. To grasp this, it helps to start with something familiar. Imagine standing on a beach, and suddenly you notice a friend struggling in the water. You want to reach them as quickly as possible. The direct line between you and your friend looks obvious. Just run straight in and swim. But there is a complication. You run much faster on the sand than you swim in the water. So perhaps you should sprint further down the beach before entering the sea, shortening your time in the water even though it lengthens your total distance. The problem becomes a balance between two competing factors: speed on land and slowness in water. The fastest route turns out to be neither the shortest nor the longest, but something in between, shaped by the ratio of running to swimming speeds. Mathematically, this is the same principle that governs the bending of light as it moves from one medium to another. Light, in a sense, faces the same dilemma: how to minimize travel time when moving at different speeds in different regions. And miraculously, light always takes the optimal route, as if it knows in advance which path will deliver it to its destination fastest. This uncanny behavior tempts us to think light has foresight, but physicists resisted such anthropomorphic illusions. The traditional explanation is that light departs from its source in a particular direction, and upon encountering a new medium, its interaction with atoms at the boundary alters its course. By strictly following local rules, it appears to obey a global principle. Nothing mystical, nothing intentional, just particles bumping into atoms. Yet the deeper one looks, the more this neat story unravels. Because in quantum mechanics, light is not merely reacting locally. It is as if the photon genuinely samples every path: straight lines, curves, zigzags, even bizarre loops through space and time. And only when the sum of all these paths is considered does the familiar trajectory emerge. What we perceive as a single, predictable line is not a fundamental truth, but an illusion born of interference. The tool that captures this strange logic is called the action, a quantity that at first glance seems arcane, but has become one of the most unifying principles in all of physics. In the 18th century, Pierre-Louis Maupertuis proposed that nature is economical, that physical systems behave as if they minimize a quantity he called action, defined as mass times velocity times distance. His idea was half intuition, half metaphysical guesswork, but it planted a seed. Later, William Rowan Hamilton formalized the concept, showing that action can be expressed as the integral over time of kinetic energy minus potential energy. With Hamilton's formulation, physicists had an alternative to Newton's laws. Instead of forces pushing particles along trajectories, one could find the path by asking which route minimizes the total action. This principle of least action proved to be elegant and powerful, a shortcut through the thickets of cumbersome equations. Still, it seemed like a clever mathematical trick, not a revelation about the foundations of reality. That changed with the birth of quantum mechanics. At the turn of the 20th century, physics was shaken by experiments on thermal radiation. Electric lighting was spreading through cities, and engineers in Germany sought to understand how glowing filaments produced light. The problem was framed in terms of a perfect blackbody, an ideal cavity that absorbed all radiation falling upon it and re-emitted radiation purely as a function of temperature. Experiments showed a curious pattern. At low temperatures, materials emitted mostly infrared, while at high temperatures, the spectrum shifted toward visible and ultraviolet. But when physicists tried to explain this distribution with classical theory, they ran into a disaster. According to the Rayleigh-Jeans law, the intensity of radiation should increase without bound at shorter wavelengths. This absurd prediction, known as the ultraviolet catastrophe, implied that any hot object should flood the universe with infinite energy. Clearly, something was wrong. Into this puzzle stepped Max Planck. He had been advised as a young man that physics was a closed field, with only minor problems left to polish. Yet in wrestling with black-body radiation, he realized classical assumptions could not survive. In a desperate move, he proposed that energy was not continuous but came in discrete packets, quanta, each proportional to the frequency of irradiation. E equals hf. Here, h, Planck's constant, emerged as a new fundamental constant of nature, a quantum of action. Planck himself was uneasy about this solution, treating it as a mathematical fix rather than a physical truth. But the success of his formula was undeniable. It matched the experimental spectrum perfectly. The strangeness of Planck's proposal deepened when Albert Einstein extended it in 1905. He argued that light was not just waves, but actual particles, photons, each carrying a quantum of energy. This explained the photoelectric effect, where light ejects electrons from metal only if its frequency exceeds a threshold, regardless of intensity. Suddenly, the quantum was no longer a trick. It was a feature of reality. Light, the most familiar of phenomena, came in indivisible units, each linked to action. Soon, quantization spread to other domains. Niels Bohr proposed that electrons orbiting nuclei could occupy only discrete angular momenta, given by integer multiples of h divided by 2 pi. His model of the atom, though crude, explained spectral lines that had baffled experimenters. Louis de Broglie carried this reasoning further, suggesting that if light could behave like particles, then matter itself could behave like waves. Electrons, protons, even entire atoms, he proposed, possessed wavelengths, and their allowed orbits were those that formed standing waves around the nucleus. The physical reason behind quantization was no longer arbitrary, but tied to interference. Only those orbits that reinforced themselves could persist. At this point, the world of singular, deterministic trajectories was crumbling. If electrons were waves, then sending them through 2 slits meant they had to traverse both slits simultaneously, interfering with themselves. The iconic double-slit experiment crystallized the paradox. Particles behaved as if they explored all options at once, and only the interference pattern revealed their presence. This was not a metaphor, but a measurable fact. And if electrons could do it, why not larger particles? Why not, in principle, everything? The difference lay only in scale. For massive objects, the action is enormous compared to Planck's constant, so the multitude of paths cancel except for those clustered tightly around the classical trajectory. But for small particles, the range of viable paths broadens, and the classical illusion dissolves. What Richard Feynman later did was to embrace this logic completely. In his path integral formulation, he declared that the true description of nature is that every particle takes every possible path, each weighted by a phase determined by its action. To compute the probability of an outcome, one sums over all these contributions. Most cancel, but the survivors cluster around the least action path. Suddenly, Maupertuis's hunch and Hamilton's formalism were not just alternative methods, but the very skeleton of quantum reality. What makes the quantum picture so unsettling is the way it undermines our instinct for locality. In the classical view, what happens at one place depends only on immediate surroundings. A ball bounces off the ground because of a collision right there at the point of contact. A light ray bends when it strikes water because of how electromagnetic waves interact with molecules at the boundary. Each event is local, and the path that emerges is the consequence of those local rules. But in the quantum view, the explanation stretches beyond locality. The very notion of a photon choosing its direction becomes misleading. Instead, it is as if the photon simultaneously attempts all possibilities, and what we observe is the interference pattern formed by this superposition. The mathematics of action clarifies why only certain paths survive. To each path, one associates a phase, a rotating arrow whose speed of rotation depends on the action. The action is measured in the same units as Planck's constant. So dividing action by h gives the number of rotations the arrow completes. For typical macroscopic systems, the action is colossal compared to h, meaning the phase rotates wildly from one path to the next. These wild rotations ensure that paths far from the extremal one cancel out when summed, their arrows pointing in every possible direction. Only the paths near the least action trajectory rotate slowly enough that their arrows reinforce one another. This is why macroscopic objects appear to follow definite trajectories. All other options cancel into oblivion. But scale things down to the size of electrons or photons, and the picture shifts dramatically. Their actions are comparable to h, so the phases of neighboring paths do not swing so violently. A broader range of trajectories survive, and the result is a blur of possibilities, a probabilistic spread rather than a single line. Quantum mechanics, then, is not an abandonment of the principle of least action, but its expansion. It shows us that the classical path is merely the sharp limit of a deeper principle, one in which all paths are real in the sense that they contribute to the outcome, but only some survive the ruthless filtering of interference. This idea echoes through the history of physics like a refrain. Planck introduced h as a desperate measure, a constant without interpretation. Einstein treated quanta as particles of light, introducing discreteness into what had seemed like a smooth wave. Bohr quantized angular momentum to explain atomic structure, though without a true foundation. De Broglie imagined matter itself as wave-like, giving quantization a natural basis. And then Feynman closed the circle by showing that all of these insights fit within a single principle. Every trajectory exists, weighted by its action, and the sum gives reality as we observe it. It is no exaggeration to say that this way of thinking reshapes our understanding of causality. If a photon emitted from a distant star reaches your eye, it has not followed a single straight path across space. Instead, it has simultaneously traveled every conceivable route, including absurd detours around planets and loops that backtrack in time. The only reason you see a sharp image of the star is that the vast majority of these paths cancel out, leaving behind the overwhelmingly reinforced signal of the classical path. The photon's journey is not a line, but a tapestry of possibilities, most of which self-destruct in interference, a few of which survive to paint the world as we see it. This principle becomes even clearer when demonstrated in experiments with diffraction. A beam of light striking a grating with thousands of slits produces bright fringes, places where waves reinforce each other, and dark gaps where they cancel. Feynman's method explains this not as an optical trick, but as the sum over paths. Each slit contributes arrows, and the geometry of the grating arranges those arrows into order. Where they align, we see brightness. Where they diverge, we see darkness. But the underlying logic is the same whether we use a grating or not. Even in empty space, light traveling from source to detector must be thought of as passing through an infinity of slits, every conceivable path across the vacuum. The grating simply makes the hidden interference visible. The philosophical implications are as haunting as the physics. For centuries, determinism reigned supreme. Given initial conditions, the laws of motion dictated the future with precision. Laplace imagined an intellect vast enough to calculate the entire universe, knowing all positions and velocities, and thus predicting every event. Quantum mechanics shattered that dream. The future is not a single trajectory waiting to be calculated, but a haze of possibilities, their interference sculpting the probabilities of outcomes. Certainty gives way to likelihood, and the universe is no longer a clockwork, but a chorus of competing paths. What makes this even more intriguing is that the principle of least action provides not only the skeleton of quantum mechanics, but also the unifying language of modern physics. When physicists construct theories today, they do not begin with forces or particles, but with Lagrangians, mathematical objects that encode how action is computed. From the Lagrangian, one can derive equations of motion, conservation laws, and symmetries. Classical mechanics, electromagnetism, special relativity, quantum field theory, all are written in this same language. The dream of a theory of everything is, in essence, the search for the ultimate Lagrangian, the correct formula for action from which all phenomena will unfold. Consider what this means for our everyday sense of reality. When you drop a stone, you see it fall in a smooth arc. What has actually happened, if quantum mechanics is to be believed, is that the stone has explored every possible descent, falling sideways, looping upward, pausing in midair, even darting through the Earth's core. These fantastical paths exist not as alternate universes, but as essential contributors to the probability of what you do observe. They cancel each other out, leaving behind only the classical arc. But their ghostly presence is what enforces the laws we trust. Reality, then, is not the path we see, but the harmony of all paths, most of which never make it to visibility. It is tempting to regard this as an exotic curiosity of electrons and photons, but the framework of path integrals applies to everything. Molecules vibrating in a crystal, planets orbiting the sun, even you as you move across a room, all are described by the same principle. The difference lies in scale. Your action, measured in joule seconds, dwarfs Planck's constant by orders of magnitude, so only paths unimaginably close to the least action route matter. The interference is so sharp that you appear to follow a single trajectory. But zoom in far enough, reduce the action small enough, and the blur of possibilities widens until the classical path dissolves into quantum haze. The laws we treat as rigid are in truth approximations carved by interference. The history of blackbody radiation exemplifies how stubbornly classical physics resisted this revelation. The ultraviolet catastrophe was not a minor error, but a breakdown at the very core of the theory. Planck's quantum of action was not merely a patch, but a rupture in the edifice. By discretizing energy, he violated the cherished assumption of continuity. Yet only by this violation did theory match experiment. And once that step was taken, physics could not turn back. The quantum had entered, and with it the necessity of accepting that nature does not unfold in single, continuous lines, but in quanta of action, in sums over histories. Perhaps the most mind-bending consequence of Feynman's formulation is the idea that paths outside our intuition also contribute. When summing over histories, one must include trajectories that defy classical constraints, paths faster than light, paths that loop backward in time, paths that wander into regions of space we think are irrelevant. These paths do not survive in the final tally because their phases cancel, but their inclusion is essential. The mathematics demands that we consider them, and only after summing them all can we explain why the classical path emerges. To exclude them would be to blind ourselves to the mechanism of interference. The bizarre is not optional in physics. It is required, if only so that the bizarre cancels itself away. At first, this seems wasteful. Why should reality bother with all these impossible routes if only one survives? But that way of phrasing it misleads us. Reality is not computing in the way a machine does, trying options until it finds the right one. Reality is the superposition of all options, the sum of all amplitudes. The least action path is not chosen after comparison, but revealed by the interference of all possible contributions. Nature does not select, it resonates. To live in such a universe is to accept a new kind of mystery. Our perception gives us the illusion of solidity, of certainty, of singular histories. Physics, when trusted to its deepest logic, shows us something stranger. That solidity is the shadow of interference, that certainty is the product of cancellation, and that the path we see is the survivor of a cosmic competition among infinities of possibilities. To trust quantum mechanics is to embrace this strangeness, not as metaphor or allegory, but as the genuine architecture of reality. The idea that every particle explores all possible histories reframes not only physics, but also our notion of information. When we think of information in the classical sense, it is tied to state. A ball is here, moving at this velocity. A photon travels in this direction with this frequency. Knowledge is a catalog of definite properties. In quantum mechanics, however, what exists is not a catalog, but a wave of possibilities. And information lives not in fixed values, but in amplitudes and phases, in the coherence between alternatives. The state of a particle is not a single point, but a superposition, a distribution spread across all potentialities. The double-slit experiment epitomizes this. Send electrons one by one through two slits, and each leaves a mark on a detector. If electrons were classical, they would accumulate in two neat bands, each representing a path through one slit or the other. Instead, after many repetitions, an interference pattern emerges. Bright fringes where paths reinforce, dark fringes where they cancel. Each electron, indivisible and discrete, behaves as though it has traversed both slits at once. Try to measure which slit it really went through, and the interference vanishes, the distribution collapsing into classical bands. The act of measurement destroys coherence, enforcing a singular trajectory at the cost of erasing interference. The lesson is stark. The world is not made of particles following single routes, but of amplitudes weaving together. And what we call observation is a violent act of pruning the superposition into one outcome. Feynman's sum over histories formalism does not merely explain this. It makes it inevitable. The path integral says that the amplitude for a particle to go from point A to point B is the sum of contributions from all possible paths. Each path contributes a complex number whose phase rotates according to the action along that path. When paths differ wildly in action, their contributions cancel. When they cluster near stationary points of action, their contributions align. The interference pattern is thus nothing mystical, but the geometry of action itself. What shocks us is that nature does not skip steps. It includes all paths, even those absurd, faster-than-light loops or backward-in-time excursions, because only their cancellation yields the observed regularities. This perspective rescues physics from paradoxes while simultaneously multiplying them. For example, in classical optics, we say light reflects off a mirror at equal angles because it is the shortest path in time. In quantum optics, we instead some amplitudes for all paths bouncing off every point on the mirror surface. The resulting interference pattern shows that the overwhelming contribution comes from paths near the classical reflection angle, and the others cancel. What appears as a local rule is actually a global outcome of interference. In everyday life, we perceive only the survivors of this massive cancellation. The neatness of our world, the apparent clarity of cause and effect, is an emergent illusion generated by the mathematics of action. The philosophical depth of this realization becomes clearer when we consider what it means for determinism. In Newton's universe, given initial conditions, the future unfolded inexorably. In Feynman's universe, given initial conditions, the future unfolds as a weighted chorus of all that is possible, most of which cancels, some of which survives, with probabilities determined by interference. There is determinism in the equations. The path integral is precise, but the determinism governs probabilities, not certainties. The unpredictability of individual events is not ignorance of hidden details, but a fundamental property of reality. No deeper variables lurk beneath, at least none consistent with experiments that have tested the very fabric of quantum theory. This is why the principle of least action holds such a peculiar place. On the one hand, it looks teleological, as if systems aim to minimize action, as if nature knows where it is going in advance. On the other hand, in the path integral, it is not teleology, but statistics. The least action path emerges as the place where contributions align constructively. There is no foresight, no planning, only interference. Yet to us, locked inside the illusion of macroscopic definiteness, it still appears as though the world chooses the optimal path. Our intuitions about purpose and efficiency are shadows cast by the deeper quantum logic. The history of how physicists came to accept this strangeness reveals how hard it was to relinquish classical instinct. Planck thought his quantum hypothesis was a stopgap. Einstein introduced photons, but remained skeptical of wave function superpositions for the rest of his life. Bohr embraced complementarity, but offered philosophy rather than mechanism. Schrödinger devised his wave equation, but recoiled from the idea of cats both dead and alive. Feynman, in contrast, accepted the weirdness unflinchingly, treating the bizarre as baseline and building a formalism where it is not an anomaly but the norm. His diagrams, his path integrals, his irreverent explanations, these were acts of surrender to nature's actual behavior rather than attempts to preserve human intuition. Once you accept this perspective, it changes how you look at even mundane processes. A photon reflecting from a mirror does not bounce at a point, but explores reflections from every atom in the mirror's surface. A molecule vibrating in your body is not confined to one trajectory, but resonates across all allowable paths. Even the particles that make up your neurons, your thoughts, your consciousness, are enmeshed in this superposition of histories. The solidity of experience is born of interference, not of singularity. Your very sense of self depends on paths you never see, paths that cancel to leave behind the narrow thread of continuity you call identity. The scale dependence of quantum behavior also explains why we are not constantly bewildered by surreal phenomena. For objects large enough that their actions dwarf Planck's constant, interference filters the universe down to near classical certainty. Only when we probe systems small enough, photons, electrons, atoms, do we witness the haze of possibility that underlies everything. The boundary is not sharp but practical. When decoherence from environmental interactions destroys the delicate phase relations between paths, the quantum blur collapses into classical definiteness. The macroscopic world is not separate from the quantum, but is what remains after relentless interference erases almost all traces of superposition. Yet even in this macroscopic world, traces of the quantum persist. Lasers, transistors, superconductors, quantum dots. The entire edifice of modern technology rests on principles born of path integrals and quantization. Without Planck's act of desperation, without Einstein's photons, without Feynman's sum over histories, the digital universe we inhabit would be impossible. The quantum strangeness we may try to relegate to laboratories and thought experiments is, in truth, the foundation of the global web of information on which civilization now runs. There's something humbling in realizing that the neat laws we learn in school, Newton's equations, the reflection of light, the arcs of projectiles, are not ultimate truths, but approximations carved by interference. They work so well because for the scales of our senses, the least action path dominates so completely that the rest is invisible. But the underlying mechanism is never gone. Even the path of a falling apple, the absurd possibilities exist. The apple arcing into space, the apple tunneling through the earth, the apple reversing time. These paths are all there, their phases spinning wildly, their contributions canceling in the sum. What survives is the path Newton described, not because nature chooses it, but because interference leaves us nothing else. To trust quantum mechanics is to accept that this strangeness is not decoration, but foundation. It is to see in every event, every reflection, every orbit, the silent chorus of infinities of paths. It is to understand that certainty is an emergent property of cancellation, and that possibility is the true fabric of the world. And it is to admit that what we call reality is less a line and more a cloud, less a trajectory and more a resonance of action. The most striking feature of Feynman's formulation is its audacity, where classical mechanics seeks the one true path, where even quantum wave mechanics tries to tame uncertainty into smooth functions. The path integral demands that we consider everything, every zigzag, every detour, every impossibility. It is a democracy of trajectories, each granted a vote in the outcome, weighted only by the phase of its action. The result is not chaos, but order, not incoherence, but the laws of physics themselves. Out of the infinite assembly of absurdities emerges the clarity of motion, as though reality were composed not of certainties, but of cancellations. To appreciate the depth of this approach, imagine splitting space and time into infinitesimal pieces, so that every path is represented as a sequence of straight segments. Each tiny segment contributes a phase depending on its kinetic and potential energy, and when you multiply them together, you obtain the contribution of the whole path. Summing over all possible sequences, you recover the amplitude for the particle's journey. This is not an approximation. In the limit of infinitely many infinitesimal segments, it is exact. The action becomes a language of phases, and interference becomes the logic by which the universe decides what we see. The power of this method lies not only in its elegance, but in its universality. Whether describing photons in an optical experiment, electrons in a semiconductor, or quarks bound inside protons, the same principle applies. All histories contribute, and interference sculpts the outcome. This universality is why physicists speak of a Lagrangian as the heart of theory. Write down the correct Lagrangian, compute the action, and the path integral tells you how reality unfolds. The differences between classical mechanics, electromagnetism, or quantum chromodynamics are not differences of method, but of the form of the action. The framework is the same, only the ingredients vary. This perspective also explains why the principle of least action, discovered centuries before quantum mechanics, feels so uncanny. Maupertuis, Hamilton, and others stumbled upon a truth larger than they could have imagined. To them, least action was a principle of efficiency, a way to solve problems with fewer equations. To us, after Feynman, it is revealed as a shadow of a deeper law. The interference of all possible paths leaves only the extremal ones visible. The principle is not teleology, but mathematics, not purpose, but probability. Its apparent foresight is the emergent effect of cancellation. The implications ripple into philosophy. If every particle explores all paths, what does that mean for free will? On one hand, the mathematics is deterministic in its probabilities. Given initial conditions, the amplitudes evolve inexorably. On the other hand, the outcome of a specific event is uncertain, irreducibly so. When you decide to raise your hand, the neurons in your brain are composed of particles whose paths include all possibilities, but decoherence ensures that only one macroscopic action survives. Your sense of choice may emerge from this pruning of possibilities, from the way interference filters the haze into a single experience. Free will in this light is not negated but reframed. It is the phenomenological shadow of quantum branching, the lived reality of one trajectory among many that were momentarily real. At the same time, the path integral reorients how we understand causation. In the classical picture, cause and effect march in sequence, each event following from the last. In the quantum picture, every path includes not only forward motion, but also backward loops, excursions into absurd velocities, even hints of retrocausality. Though these paths cancel in the end, their temporary inclusion suggests that causation is not as rigid as intuition insists. The arrow of time, so firm in macroscopic experience, may itself be a product of interference, a statistical outcome of overwhelmingly large actions. At the quantum level, time is not a line, but a weave, and causation is not a chain, but a resonance. This way of seeing also reshapes how we think of space. If particles explore all paths, then in a sense, every point in space is connected to every other. The amplitude of connection may be tiny, cancelled by interference, but it is never exactly zero. This is why tunneling occurs. A particle can appear on the far side of a barrier not because it has violated a law, but because the paths that cross the barrier, though improbable, contribute faintly. In the classical world, barriers are walls. In the quantum world, they are filters. Nothing is ever completely disconnected from anything else. Such insights make clear why quantum mechanics has been so fertile for technology. Transistors rely on tunneling, lasers on coherence, superconductors on collective quantum states. Quantum computers promise to exploit superposition and interference directly, summing over many paths in parallel to solve problems intractable for classical machines. These technologies are not curiosities, but direct applications of Feynman's vision. Trust the sum over histories, and you can harness the strangeness of the world. The path integral also offers a lesson in humility. For centuries, physicists tried to force nature into the mold of human intuition. forces, particles, trajectories, certainties. Quantum mechanics shows that the universe is stranger than our imagination, yet also more coherent. By abandoning the comfort of singular paths and embracing the fullness of possibility, we discover a framework that unites the smallest scales with the largest. From the spin of electrons to the orbits of galaxies, the same principle applies. Action determines phase, phase determines interference, interference determines reality. Even in cosmology, this perspective plays a role. Some physicists have speculated about the sum over universes, an extension of the path integral to the entire cosmos. In this view, the universe itself explores all possible histories, and the reality we inhabit is the survivor of interference among them. This idea remains speculative, yet it reflects the audacity of Feynman's method. Once you trust quantum mechanics, you must accept that nothing is too strange to be considered. If particles explore all paths, why not universes? If interference sculpts electrons, why not cosmologies? And yet, for all its strangeness, the path integral restores a kind of simplicity. It tells us that the bewildering array of phenomena we observe are not governed by separate rules, but by one principle expressed in different forms. The diffraction of light, the stability of atoms, the tunneling of electrons, the arcs of planets, all are echoes of the same logic. The differences of scale obscure the unity, but the mathematics reveals it. Trusting quantum mechanics means recognizing that unity in disguise, that order within apparent chaos. There is a beauty in this vision, a beauty that lies not in simplicity of picture, but in depth of coherence. To say that a photon explores all paths is not to invoke mysticism, but to describe with precision how amplitudes add. To say that an electron is both wave and particle is not contradiction, but recognition that categories must expand. To say that reality is probability is not defeat, but acknowledgement that certainty is too brittle to carry the weight of the world. The beauty lies in seeing through the illusions of singularity to the richness of possibility, and in discovering that possibility itself is ordered by action. The more deeply one reflects on the principle of all paths, the more it reshapes the imagination. We are trained by perception to think in terms of straight lines and singular events, but underneath lies a web where everything is connected through possibility. A photon's journey across space is not a line, but a cloud of alternatives. An electron bound in an atom is not a bead circling a nucleus, but a standing wave resonating with itself. Even the ground beneath our feet is held together not by rigid particles, but by fields whose excitations obey the strange arithmetic of interference. The solidity of the world is a construction of cancellations, a harmony that hides its discordant notes. To see the universe this way is to recognize that certainty is an illusion. When you look into a mirror, you trust that the reflected image corresponds to a single path of light bouncing from your face to your eyes. But the reflection exists only because countless paths across the mirror's surface interfere, most canceling, a few reinforcing. What you see is not the triumph of one trajectory, but the survival of a pattern. Even the image of yourself is the residue of paths you will never know. And if this is true of light in a mirror, it is true of everything. The pen in your hand, the stars in the sky, the memory of yesterday, all are woven from the interference of histories, most of which have been annihilated in silence. This perspective carries ethical as well as scientific weight. If reality is not a single path, but a superposition, then every outcome we witness is not inevitable, but one survivor among many possibilities. The world is not fixed until interference filters it. That means our future, too, is not a line waiting to be traced, but a haze of trajectories, some aligning, others canceling. Our choices, our actions are part of this interference, shaping probabilities even if they cannot command certainties. To act is to tilt the balance of amplitudes, to add weight to one cluster of paths rather than another. This is not mystical, but profoundly physical. Human beings, made of particles, participate in the same sum-over histories as photons and electrons. In this sense, Feynman's vision offers a profound metaphor for living. Each moment is a crossroad of infinite possible paths, most of which will cancel, but some of which may align into a trajectory that endures. To trust quantum mechanics is not only to accept the strangeness of physics, but to embrace the openness of life, the idea that the future is not predetermined but sculpted by interference. Just as particles explore every route, we too explore possibilities through thought, choice, and chance. And just as nature reveals its laws through the survival of least action paths, our lives reveal their meaning through the coherence of actions that reinforce one another into a pattern. This does not diminish the grandeur of physics, it enhances it. For the principle of least action, far from being a trick of mathematics, becomes a philosophy of being. It tells us that efficiency and elegance are not imposed on the universe, but emerge from its structure. The path that survives is not the one chosen by foresight, but the one revealed by harmony. To live is to participate in that harmony, to find resonance among the infinite cancellations of possibility. Consider again Planck, despairing at the problem of blackbody radiation. He did not set out to revolutionize physics, but to solve a technical puzzle. Yet his act of desperation, quantizing energy, turned out to be the seed of a new worldview. From his constant H came Einstein's photons, Bohr's quantized orbits, de Broglie's matter waves, Schrödinger's equation, Feynman's path integrals, and the entire edifice of modern physics. The constant that seemed a nuisance became the measure of reality itself. Planck called it a quantum of action, and perhaps no phrase captures the spirit of physics better. Action, the integral of energy over time, is the true currency of the universe, and H is its smallest unit. When physicists seek new theories today, quantum gravity, string theory, unification of forces, they do not hunt for new forces in the Newtonian sense, but for new actions, new Lagrangians whose interference will produce the universe we see. The hope for a theory of everything is the hope for a single action principle encompassing all. That search is not over, and perhaps it never will be. But the path integral provides the compass. Whatever the ultimate theory, it must be expressible as a sum over histories, as interference of action. Anything less would betray the coherence nature has already revealed. And yet, the deeper lesson is not just scientific, but existential. To realize that the world is built not from certainty, but from probability, not from singularity, but from superposition, is to recognize that our place within it is both fragile and astonishing. The reality we experience is the survivor of interference, a thin thread woven from infinities of canceled paths. The fact that anything is visible, tangible, coherent, is a miracle of alignment. To exist is to be the constructive interference of possibility. Feynman once said that no one truly understands quantum mechanics, and perhaps that will always be true. But to trust it, to let it guide our vision, is to glimpse a universe more subtle and more mysterious than common sense allows. It is to see that the principle of least action is not a convenience, but a revelation, that particles do not move but resonate, that reality is not chosen but summed. And in that vision lies a kind of beauty, a recognition that strangeness is not a flaw in the universe, but its essence. When you next look at light reflecting off water, or when you watch an apple fall, or when you gaze at the stars, remember that what you see is not a single path, but the survivor of infinite cancellations. Remember that certainty is an illusion crafted by interference, that behind every image lies a haze of possibilities. Remember that action is the language of the universe, and that every particle, every field, every thought you have is woven into the sum over histories. To trust quantum mechanics is to accept this strangeness as reality, to live not in the comfort of singularity, but in the richness of possibility. And so the journey comes full circle, from the beach thought experiment to the mysteries of blackbody radiation, from Planck's desperate guess to Feynman's bold formulation. The lesson is the same. Nothing moves along a single line. Everything explores, everything resonates, everything interferes. What we see is the survivor of that interference, the path of least action revealed not by foresight, but by harmony. This is the strangeness we must trust, that the universe is not what it seems, and yet, through the coherence of action. It is more comprehensible than we ever dreamed.